Hello, everyone. Let's continue our discussion on training models. We'll discuss polynomial regression. So we wrapped up linear regression using multiple methods, including normal equations, SVD, and gradient descent methodologies. And there are multiple variants of gradient descent methodologies. And as a natural extension for linear regression, it's going to be polynomial regression. So what is polynomial regression? So what we're trying to do in polynomial regression is we can use a linear model to fit nonlinear data. The way that you do it is you can leverage a polynomial features class coming from sklearn pre-processing. And the way you could essentially what it's trying to do is you have a feature x. We're trying to generate second degree polynomial, for example. We're trying to generate x squared. If we have multiple dimensions features, x1, x2, x3, and then we're trying to generate x1 squared, x2 squared, x3 squared, and also interaction terms of x1 times x2, x1 times x3, x2 times x3. So by doing that, we have multinomial terms, and with the hope that with all the multinomial terms, we are able to fit the model as well. So essentially, we can still leverage linear regression model. The input is no longer the feature itself. It is coming from X poly. X poly is a transformed features, including higher degree of polynomials. So essentially, we're fitting a function of y in terms of x1 squared, x2 squared, x3 squared, but the function form is linear. X is pre-processed to have a polynomial term. And then after fit, in this example, you can see that an intercept is 1.78 with two coefficients. One is 0.93, the other one is 0.556. So what does that indicate? That essentially says we can use a model estimate of second degree polynomial x 0.56 x1 squared plus 0.93 x1 plus 1.78. In this example, we only have one feature, which is x1. Then the output of the function is a second degree polynomial. And so essentially, you're using this x1 squared as one specific feature, which is a transformed variable of x1. And fit, if you look at the numbers again, 0.56, 0.93, and 1.78. 1.78 is the intercept. And one of them is for second degree polynomials. The other one is for first degree feature itself. And then let's look at the original function, right? Original function is coming from randomly generated data set, which is coming from 0.5 x1 squared plus 1.0 x1 plus 2.0 plus Gaussian noise. So you can see that, this fit is really not bad at all. It somewhat fits the data reasonably well. So what if we increase the degree of higher the degree of polynomial regression? So for high degree polynomial regression, you can see here for 300 degrees, which is a green line, is trying to fit the data very, very much well, trying to connect trying to capture pretty much every single change of what the model sees from the data. And then on the other end, for 1 degree, which is a linear function, which is a red lines, and also second degree would be the blue lines. You probably would already be aware for the green line, it's just running the risk of overfitting because it's trying so hard, the model is trying so hard to fit every single change of the data. Here just give you understanding and illustration of different degrees of polynomial regression. Let's look at the learning curves. So let's say you can leverage linear regression model, and then you just plot learning curves using the input x and y as well as the model itself. And then just by doing this, this is our learning curves. What you saw here is for the blue, which is the validation data set, versus the training data set. And see that in general, both of them are still generating high IMSE, which is around 2. Whether it's high or not really depends on the unit of the original data. So you should look at what's the data, distribution of the data, and see, comparably speaking, whether the IMSE is small or large. That's something you should definitely pay attention when you're trying to evaluate your model or when you're working on your project as well. Let's look at 10th degree polynomial model, the learning curves. Now this one is giving us a slightly different story, right? One is the IMSE is smaller than what we saw in the previous slide, which was around 2.5. The second thing you'll find that there is a gap between the validation set and the training set. We were hoping that the validation set is doing as decent job as the training set. So in this case, we almost sure that you want to do a little bit better for your training data set so that we could narrow down that gap. In other words, there is a chance that the model is underfitting. Let's try to enhance the model a little bit more. Now, this is really a natural segue to what we usually use in machine learning. That's called the bias variance trade-off. This is very important. For any of the machine learning algorithms, you should pay attention to the bias and variance trade-off. Let's look at what that is. It is an important theoretical result of statistics and machine learning is the fact that a model's generalization error can be expressed as a sum of 3 very different errors. So first question you have probably would be, what is generalization error? Generalization error, we're talking about not only the training, but also whether the model can do a decent job on those unseen data. If it's going to do really well on the unseen data, then we think that model is generalization capability is reasonably well. Otherwise, we think the model is not doing a decent job on generalization. So let's look at specifically what are those components. One component is called bias. This part of the generalization error is due to wrong assumptions, such as assuming that the data is linear when it's actually quadratic. A high bias model is most likely to underfit the training data. That's called bias. It's essentially saying that your model is not doing a decent job just by looking at the bias, if it's too high. How about variance? Variance's part is due to the model's excessive sensitivity to small variation in the training set. A model with many degrees of freedom, such as high-degree polynomial model, is likely to have a high variance and thus overfit the training data set. overfit the training data set with smaller bias, but tend to have a higher variance. On top of those two types, it is one type of error that you can't just get away from, that is called irreducible error. This part is due to the noisiness of the data itself. The only way to reduce this part of the error is to clean up the data. Fix the data sources such as broken sensors, or detect or remove outliers. Increasing model's complexity will typically increase its variance and reduce its bias. Again, conversely, reducing the model's complexity would increase its bias and reduce its variance. This is why we call it as bias and variance trade-off. So from next page, you probably would even understand even better. So what exactly is bias and variance trade-off? For example, for this chart on the top left, it has low bias and low variance. So saying that we're shooting the target, and majority of the time we're right on the target, and it's also concentrated on the target. It's called low variance and low bias. How about the one on the bottom left? You kind of still concentrated. You're trying to shoot the target. Your results are still concentrated in one area, but it is kind of off the target. So in this case, we consider it still have low variance, but it's really not doing a decent job to find the target. So that's called high bias. How about the other way? Let's look at the one on the top right. It has low bias. So it's kind of close to your target, but it has a lot of variance. Some of them are a little bit further away from different directions. Then that's called low bias and high variance. And then high bias and high variance, bottom right. So it's not only scattered around, but also it's far from the target. If it's close to the target, we call it low bias. It's far from the target, we know it's going to be high bias. If it's even scattered around, then we also call it as high variance. So that's high bias and variance trade-off. In terms of model complexity, this graph tells you even better. So what it says is x-axis is the model complexity and the y-axis is error. So we're suggesting that as you increase your model complexity, your bias tend to decrease. You're trying to fit your data so well, trying so hard to fit that data. As a result, the bias becomes smaller and smaller. So if you think about linear regression versus polynomial regression, if you have higher degree polynomial regression, essentially we're trying to increase the model complexity. 1 versus 20 degrees of polynomial, then we're increasing the model complexity. By doing that, you are going to decrease the model bias. However, if your model is so complex, you have low bias, but the model cannot be generalized well, meaning for some unseen data, the model is not going to do a decent job. That's exactly what's happening on this green line as the variance becomes higher. So as model becomes more complex, the bias is smaller, but variance tend to be bigger. As a result, for our model, what we're after is a model that can decrease the total error. The total error is the bias plus variance. So we're trying to figure out the optimum model complexity that can help us to find the minimum of this total error. Of course, here we actually didn't include the irreducible error just because it's something that you cannot do anything about. we can only try to, from the modeling perspective, we can only try to control bias and variance. So this is an important chart, right? So does it mean that the more complex model would be better? No, not necessarily. Does it mean that the simpler the model is, the better? No, not necessarily. Because when the model becomes too complex, you tend to overfit your data, and it doesn't have it's going to tend to have this lack of generalization capability, and as a result, it have a higher variance. Again, we're trying to find the model complexity that can generate the minimized total error. Okay, this actually concludes our discussion on polynomial regression and bias and variance trade-off. Thank you.